Um, what's that?
The homework that was due today, were like the last few questions, like, have we gone over that yet, like the critical depth and stuff?
Yeah, critical depth, remember, is you'd set the Froude number to 1 and solve for y.
Okay.
Yeah. We'll talk more about it today, but the thing that I think will be new information today is talking about critical slope. And there wasn't a critical slope question on the homework, was there?
No.
All right. But yeah, boy, that alarm, it's just music to my ears.
I know clear lights.
Close
Is that the door alarm or is it a fire alarm?
I don't know.
I think that's an important.
Doesn't seem like a fire alarm, right?
I would hope so.
Not loud enough.
It's every weekend too. You come here on like a Saturday.
Yeah.
What's going on?
All right, so I'm going to post homework 9 onto Blackboard today. It's only 3 problems, and it's due on Wednesday after spring break. And then on Friday after spring break is when the pipe sizing part of your project is due. And I've been working my way through the demand estimation. So far they're looking really good. Maybe best ever. I don't want to jinx anything by saying that, but like the first few that I graded were excellent. So I'm hoping that trend continues. We're going to move into chapter 12 today. And before we do, I wanted to show you one student who did a nice job with the annotations. Now this was back when I hadn't yet given the students the idea that you don't have to go to these locations where there's no flow withdrawals. So nowadays you'd probably connect C and E directly because that's where water is coming out. Back in those days they just kind of followed the city limits. But this student did a nice job of getting annotations that are about the right size given the scale of the map. You can see that all of the things that we need to know, which is like the pressure at the junction, the flow rate that's being withdrawn at a junction, the flow rate through each pipe, its length, its diameter. So all of those things are annotated in a really nice way. And I think some of it was automatic, some of it they had to just kind of manually adjust the annotations at each of the locations. But I wanted to draw your attention to the fact that it's part about getting the right pipe size, but then it's also about making the map neat and professional and kind of a reflection of all the work that you've put into the project so far. All right. Now, why do I want 2 maps? It's because one of the maps is at the maximum design flow, and one of the maps is under zero flow. And so the big difference in those 2 maps is going to be the pressures at the junctions. So under the design condition, you'll notice here this student isn't below 240 kilopascals at any of the locations in the network. And then at the condition of zero flow, what I'll be looking for is that none of your junctions have a pressure of more than 850 kilopascals. So what determines the pressure at the junctions when there's water going through the pipes is both the reservoir height and also the pipe size. But when it's zero flow, the pipe size doesn't affect the pressure at all. It's only the reservoir height and then the elevation of the junction that determines the pressure under static conditions of no flow. So any questions related to this next phase of the project before we move on?
Do you recommend doing the flowing portion first and then the zero flow? Does that help with the design?
I think it's probably better to do the flow part first and then the zero flow, but knowing where to put it's kind of iterative though, because I mean you don't want to put the reservoir at an elevation of 300 if that's going to make the pressures everywhere else too high. So, you know, I guess maybe calculating what's the maximum elevation you can go for the reservoir would be a good place to start. So actually maybe the static condition and then the flow condition.
Okay.
All right, so back to open channel flow. Critical conditions are when the Froude number is equal to 1. Remember that supercritical flow is when the Froude number is greater than 1. It's associated with shallow depths and high velocities. Subcritical flow is associated with relatively deeper depths and slower velocities. But critical conditions is here on this specific energy diagram. It's the location where the change of energy with respect to depth is 0, because we're out here at this point, the far left edge of that point. So the change of energy with respect to depth is 0, and in that condition the Froude number is 1. So keep that in mind. Now we can rearrange this Froude number equation in critical conditions when the Froude number is equal to 1. If we wanted to just algebraically adjust that, on the left-hand side of the equation we've got a constant, the flow rate squared divided by g. And on the right-hand side, we're going to have geometric parameters that are related to the flow depth. So when you have critical conditions and you're trying to solve for the depth, then you put the constants on one side and all of the unknown terms on the right. So let's just say that we've got a rectangular channel that's got a bottom width of 4 meters. So here's a canal with water flowing through it, 4 meters wide at the bottom, and its flow rate of 10 cubic meters per second. And we want to know what is the depth when conditions are critical. So y sub c. If we just say, well, critical flow is when the Froude number is equal to 1, and what we can do is substitute in the known flow rate and square it, and then express the area as a function of the unknown depth. So basically, if we've got q squared divided by g equals a sub c cubed divided by b, the top width, under critical conditions, then that's the same as saying q squared divided by g is equal to, in this particular case, 4, which is the width of the channel, multiplied by y sub c. And we're going to cube that, and then divide it by the width of the channel when conditions are critical. And for us, that is some width of 4 meters. Okay? So if we now move this over to the other side, then we've got 4 times q squared, and now let's substitute in the flow rate. The flow rate is 4 times 10 times 10, because it's q squared, so 100 on the left-hand side. And we're taking that to the 1/3 power divided by 9.81, and then that is going to be equal to y sub c. So we move the 4 to this hand side, substitute in 10, square it, and then all that's left on the right-hand side of the equation would be the y sub c, because we took this to the 1/3 power. So in doing that, we can now, y sub c calculate is going to be 0.860 meters. And this version of the Froude number equation and critical depth method is valid for any type of shape. It can be rectangular, trapezoidal, but there's going to be a simplification which I'll show you, which depends on us determining something known as the flow per unit width. And so this channel is 4 meters wide, and it's got 10 cubic meters per second going through the channel. And so the flow per unit width, Q, is Q divided by B. So it is 10 cubic meters per second going through a channel that's 4 meters wide. So that is 2.5 cubic meters per second per meter. In other words, another way we could express those units is 2.5 meters squared per second, because there's meters in the denominator, which cancels out with the meters in the numerator. So flow per unit width only applies if you've got a rectangular channel. If you have a trapezoidal channel, then it doesn't make sense to describe the flow per unit width because the edges have a varying depth. So this notion of lowercase q for the flow per unit width, only estimate that for a rectangular channel and not for a trapezoidal. So you wouldn't calculate flow per unit width here because, you know, this part of the channel is carrying less per unit width than the rectangular section. Those edge pieces don't have the same capacity, both because the depth is changing, but then also there's the issue of them being closer to where the resistance is applied with the shear stress. Okay, so if you've got flow per unit width, one way to express it is on a volumetric basis, but also you can express it as the velocity times the depth. So V times Y also gives you the flow per unit width. And that's because, remember that Q equals VA, and so we've just substituted in V times A here for Q, and divided by B. So when you make the substitution where Q equals VA, and you put that in here, then just another way to express the flow per unit width is the velocity times the depth. And are the units the same? Do you still get meters squared per second? You do, because velocity is meters per second and y is meters. So it's still a flux, meters squared per second. Now, this formula is just so tempting to use to calculate the critical depth because it's a lot easier than the full-blown equation for the Froude number set equal to 1. But if you've got a rectangular channel, then like we do here in this example, then this equation works just fine. So let's try that out. If we say that the y sub c is the flow per unit width squared divided by g to the 1/3 power, then in our case our flow per unit width is 2.5 meters squared per second. And we square that, divide it by 9.81 meters per second squared, and take it to the 1/3 power. So if you've got your calculator handy, let's just double check and see if it gives us the 0.86 meter depth that we calculated before. So 2.5 squared divided by 9.81 and taken to the power of 1/3. Yeah, 0.860 meters deep. Okay. So a lot of the problems you're going to work this semester will be rectangular channels, especially when we get into the non-uniform flow and we're trying to calculate like what is the depth some distance downstream of an obstacle. Those problems will be with rectangular channels just for simplicity's sake. And so you can use this equation a lot, but be really careful about using it only in situations when it's a rectangular channel, because we won't have flow per unit width defined in a meaningful way for anything other than a rectangular channel. So any questions about this equation or its applicability before we move on? So many people wearing ties today. It's just a different kind of atmosphere in the classroom.
I changed.
Yeah, thank you. It makes it easier for me.
Does me taking notes make you nervous?
No, I like that. All right. So we got the same depth of 0.860 meters because this channel was rectangular. Okay. Now, critical slope is what slope is required to cause critical conditions. Because remember, when we looked at our first specific energy diagram, let me just go back to a slide from Monday to refresh your memory. We had this table, and there were lots of different velocities, lots of different depths. And what I told you was that for this to be true, for you to have a flow rate of 10 cubic meters per second, and some of them with the fast velocity, some with the slow velocity, then what you would be varying to make that happen would be the slope itself. but there's some slope that would cause the critical depth, which is associated with the minimum specific energy. So that's what this next part is about, that we're talking about today, is critical slope is what is the slope that would give you a depth in the channel equal to the critical depth. So this is a rectangular channel, I'm sorry, a trapezoidal channel. You can see it's carrying 186 cubic meters per second. We've got the dimensions of the channel defined, where the side slopes are 1.5 to 1. And what we're going to try and do here is a two-part problem. First, find out what is the flow depth in this situation using Manning's equation. And then we'll find the flow depth based on the Froude number, and then we will substitute that into Manning's equation for the slope. So the side slopes being 1.5 to 1, that means that t, the parameter which is describing the side slopes, is 1.5. And so we've got a formula for the top width, cross-sectional area, the wetted perimeter, and then W, which is related to the wetted perimeter. So if we've got a t of 1.5, then that means that W is going to be 1 plus 1.5 squared to the 0.5 power, so it's 1.803. And we can calculate the wetted perimeter now that we've got that. So P, the wetted perimeter, is going to be the bottom width of 3 meters plus 2 times y, which we haven't yet calculated the depth. And so q squared times the top width b divided by g to g times a cubed is equal to 1. So when critical flow is happening, then we know the Froude number will be equal to 1. And so here we know that the flow is 186 cubic meters per second. The top width, B, is 3 meters wide plus 2 times 1.5 times y. So everything is known in the top width except for the depth y. So y that we're talking about here is the critical depth. And then G, 9.81 meters per second squared. And then the area, everything is known except for the critical depth. So B is 3 plus 1.5 y sub c times y sub c. And that is cubed equals to 1. Okay, so this is just saying when you have a Froude number of equal to 1, what is the depth that corresponds to that? And so if we put it into the solver, whether it be Excel or the calculator or an online solver, we get that the critical depth y sub c is 4.121 meters. Okay, now with that, we can go back to calculating the wetted perimeter and the cross-sectional area, which we're going to put into Manning's equation. So the wetted perimeter is the bottom width, B, 3 meters plus 2 times y. So the y that we've just calculated means the critical depth, 4.121 meters. And the W term that we calculated based on the side slope, 1.803. Okay, so then the wetted perimeter is 17.858 meters. And the other thing that we're going to need to go into Manning's equation, where the unknown will be the slope, we want to say how steep should the channel be to cause critical flow. Well, in this example, we know the roughness, N, we know the Q, the flow rate. Now that we know the depth at critical flow, we're going to substitute both of those terms in for the area and the hydraulic radius, and the only unknown is going to be the slope that's causing critical flow. Okay, so we've got the wetted perimeter. Let's also define the area. So the area is 3 plus 1.5 times 4.121 times the depth, 4.121. So b plus ty times y. So b plus ty times y. And that is, for the area, 37.837 meters squared. Okay, so we've got the area and the wetted perimeter, so the hydraulic radius, let me just segment this a little bit because we've got two different parts of the problem. This was the finding y sub c, and now we are finding the slope from the y sub c. So the hydraulic radius is the area divided by the wetted perimeter, so that is 37.837 meters squared divided by 17.858 meters. So 2.119 meters is the hydraulic radius. And we're going to put it into Manning's equation. So I'm going to rearrange Manning's equation to solve for slope. So that is, its S is N times Q divided by area times hydraulic radius to the 2/3 power. And then we square it. So that's just algebraically rearranging this equation. So N times Q, and we divide by the area, divide by the hydraulic radius to the 2/3, and then we square it. So that's isolating the slope. And so the slope under critical conditions, so S sub C means the slope that causes critical depth. We now substitute in the given N value of 0.013, the given flow rate of 186 cubic meters per second, the known area 37.837 meters squared, and then the hydraulic radius of 2.119 meters needs to be taken to the power of 2/3, and then all of that is squared. Okay, the slope that we're going to get is 0.0015. So that's 0.15%. Let me just bring up this solution onto the screen here so that it's worked into the video. One of your classmates is at a scholarship interview right now. I want to make sure that they get to see the calculations for this one. Okay. So, just to recap, what we did was use the definition of Froude number to solve for when you have critical conditions, what is the depth? And it was 4.121 meters. And then once we know the depth, we put that into Manning's equation as a known. And the only unknown is what slope causes that depth when you've got a certain flow rate and a certain roughness. And so the slope that we're going for is 0.15%. So if you want to induce the critical depth, then you'd have to have the slope of 0.15%. Now there's this terminology called a mild slope. A mild slope is any slope which is less than that. So it would mean it's more shallow or more flat than 0.15%. A mild slope will cause subcritical flow. So what do you think it's called when it is a slope that causes supercritical flow? It's steep. I wish it was called spicy, but it's not. You know, because the other one's called mild. I think it would be better if it was spicy and mild, but it's steep and it's mild. Diablo, yeah. Okay, so a mild slope would be anything that's less than 0.15%, and a steep slope is one that is anything greater than 0.15%. So steep slope is that slope which causes supercritical flow. A mild slope causes subcritical flow. So you could do this analysis and just know that, you know, here you've got a trapezoidal channel, and you're going to be carrying 186 cubic meters per second. And then depending on where you're putting it, if you're putting it in a relatively mountainous area with steep conditions and the slope is greater than 0.15%, then you'd have supercritical flow through that channel. If you had a slope of less than 0.15%, then you'd have subcritical conditions. And whether you have got subcritical or supercritical conditions is going to be important when it comes to how the water behaves when it encounters obstacles. So are there any questions about this particular example related to determining the critical slope? Okay, well, remember that this diagram is called a specific energy diagram, and we can create one for having a certain flow rate, just different combinations of depth and velocity, and each one of the locations on this curve has the same flow rate, but it's different specific energy depending on what depth and velocity the water is going at. We're going to start looking at what happens when there are varying slopes that cause these different velocities and depths. Because some channels will be relatively steep, and this picture on the left is a photo of a mountain stream that's flowing very quickly, and you can tell it's moving quick by the fact that it's got some rapids. You can see the entrained air, which it looks like white caps in the water. And a lot of the rivers and streams around here have relatively slow moving velocities, and we need to be able to analyze whether conditions are down here in the supercritical range or whether they're in the subcritical range, because when we encounter some sort of an obstacle, then the amount of energy that's lost is going to affect the flow depth differently depending on if the before condition was supercritical or subcritical. So let's take this first example of a step down. So water's flowing, and initially upstream before this drop, the flow conditions are subcritical. And the way that we can diagnose that is in this diagram. You notice that they've kind of identified with a dashed line here what is the critical depth. So y sub c is some depth, and they're telling you that the depth at location 1 is greater than yc. So without us knowing the slope, without us calculating the Froude number, just kind of by inspection, we can already know that the flow conditions at 1 are subcritical because the given depth is greater than the critical depth. So we have a subcritical flow that encounters a drop down. And what happens is that the specific energy has increased when the water drops down across a step like this. There's more energy than there was before in the magnitude of delta z. So then the water is going to react, and it's going to come into equilibrium with some new depth. It's not going to have the original depth that it had, y1, because now it's got more energy downstream because the water went off of this step down. It gained some additional specific energy. It's now going to be at a different depth. So the question in problems like this is, how deep will the water be after the step? Now, we can analyze it qualitatively with a specific energy diagram. So first you have to diagnose the flow regime upstream, and you can do that, if the diagram gives you the normal depth and the critical depth, then you can compare the two to determine whether it's sub or supercritical. or you can calculate the Froude number upstream. But we need to know at location 1 whether conditions are sub or supercritical. Now, here is the specific energy diagram, and our book has this information in it, but I'm going to kind of walk you through the steps of what we do when there's a drop and how we use the specific energy diagram to tell us the new depth downstream. So we start off with a depth at Y1 on the specific energy diagram. So you can see I've kind of toggling back and forth with that new line. So a certain depth gives you a certain point on the specific energy diagram, and you go down to find E1. So that's the amount of energy associated with that depth. So how do you find E1? Well, you can either use the diagram or you can just calculate it. Remember that E is the sum of two terms. It's the sum of the depth and the velocity head. So you can just calculate the amount of specific energy at location 1 by adding those two things together. So E1 would be Y1 plus Q squared divided by 2GA squared, or Y1 plus V1 squared divided by 2G. That's the amount of specific energy at 1. But this delta Z is going to add more energy. So what we do with this next step is we increase the amount of specific energy in the amount of delta Z to find E2. So E2 is E1 plus delta Z. So in words, the amount of energy that you have after the step down at location 2, you've got the amount of energy that there was at 1 plus delta Z. So that, I think this is pretty straightforward. E2 is just the energy that you had at 1 and a little bit more in the form of delta Z. And so now if we go up through the specific energy diagram, we now have more energy in the water. So the depth isn't going to be the same as it was before. We go up to this part of the curve. Now remember that we cross the specific energy diagram at two locations. We cross it here and we cross it there. And we're going up to the upper location because at location 1 conditions were subcritical. So the new depth downstream will also be subcritical, which is why we choose this inflection point rather than the lower one. So we go up and over, and so this is our new Y2. So we could say that if we're trying to find Y2, we need to know how much energy there was at 1, add delta Z, and then solve for the new depth, because E2 is going to be the combination of E2 is going to be Y2 plus V2 squared divided by 2G. Or the other way to express it, of course, Y2 plus Q squared divided by 2GA squared. Now, A at location 2 is going to be different than A at location 1 because they've got different depths. Even if the channel is rectangular and the width is the same, they've got different depths. And so we're going to be expressing the area in terms of the depth. So we've already talked about how with your calculator you need to be able to solve Manning's equation for a trapezoidal channel. Another thing that you're going to need to be able to do with your calculator is to solve cubic equations, because there's lots of them when we are doing these bed transition type problems. And we'll look at one just as our final example before spring break. We've got this example where water is flowing at 30 cubic feet per second, and then there's a 1.2 foot bed drop. The channel is 8 feet wide, and the initial depth is 3.5 feet. And we want to know what is going to be the depth after we go off of this drop. So it was flowing along at 3.5 feet. What will be the new drop, depth downstream? So the first thing we have to do is determine whether we've got supercritical or subcritical flow, because remember in this diagram, the delta Z is going to give us more energy, but do we use this depth, which is associated with the supercritical conditions, or this depth, which is associated with the subcritical conditions? So let's do that. Let's first assess what is the flow regime at 1. And remember, flow regime just means, is it subcritical or is it supercritical? So we've got a rectangular channel here. You could calculate, there's a couple of ways to diagnose the flow regime. You can either calculate the Froude number, or you can compare the given depth to the critical depth. Well, let's look at both. First of all, the Froude number is going to be Q squared times B divided by G A cubed, and all of that's to the 1/2 power. Okay, so at location 1, we've got our flow rate is 30 CFS, and we're squaring that. The width of the channel is 8 feet divided by 9.81. Oh no, for traditional units it's not 9.81, it's 32.2 feet per second squared, and then times the area cubed. And so the area for this one is 8 feet by 3.5 feet. So the area is 8 feet by 3.5 feet, so that is 28 feet squared. So 28 feet squared. And we cube that, and then all of this is to the 1/2 power. So the Froude number is 0.101. So the dividing line for subcritical and supercritical is a Froude number of 1. So subcritical conditions. Subcritical at 1. And let's just check that the other way. Y sub C is the flow per unit width squared divided by G to the 1/3 power. Okay, so what is our flow per unit width? Q is 30 cubic feet per second divided by the 8-foot width. So the flow per unit width is 3.75 feet squared per second. We just say that we want to know for every one of the feet of the 8 feet wide, how much flow per unit width is it carrying? 3.75 is the flow per unit width. So then 3.75 cubic feet, feet squared per second squared divided by 32.2 feet per second squared to the 1/3 power. So our critical depth is 0.759 feet is the Y sub C. So comparing Y sub C to our given depth of 3.5 feet, what does that mean the flow regime is? What's the flow regime based on the depths? Subcritical. So since Y1 is greater than YC, so 3.5 feet is greater than 0.759 feet. Because of that, thus, flow at 1 is subcritical. So either one of these establishes the flow regime at our before. When conditions were steady and uniform at location 1, it was subcritical. And that's going to be important because we're going to be solving a cube root equation. We'll have one negative root, and then we'll have two positive roots. And one of those roots is associated with the alternate depth that is supercritical. One of the roots is associated with the alternate depth that is subcritical. And we have to know which of those two roots to select. And so this first part that we've done in diagnosing the flow regime is going to tell us which of the roots to select once we get to that point of having a solved cubic equation. Okay, so is everybody okay with what we've done so far in diagnosing the flow regime at 1? Okay, so then the next part of the problem here is we're saying E1 plus delta Z is equal to E2. So we had a certain amount of energy at 1, and energy at 2 is higher than the energy at 1 because of the drop down. So let's define what we mean by that. We've got y1 plus v1 squared divided by 2g plus delta z is equal to y2 plus q squared divided by 2ga squared. So on the left-hand side, I expressed the velocity head term instead of in terms of v. On the right-hand side, I express the velocity head in terms of the flow rate in the area because it's going to involve an unknown depth at y2. So specifically, like A at location 2, A2 is just y2 times 8. So that's what I'm going to substitute in here for the area when I get to that point. But what we do know is like the flow rate at of 30 cubic feet per second, I can calculate the flow velocity because I know the area and the flow rate. So for example, V1 is going to be Q divided by A1. So A1 is, so the flow rate of 30 cubic feet per second divided by the area of 3.5 feet by 8 feet. The velocity at the first location is 1.071 feet per second. So now let's put in the numbers that we actually know. On the left-hand side, it's 3.5 feet is the depth at 1, and then the velocity head, 1.071 feet per second squared divided by 2 times 32.2 feet per second squared, plus the delta z. This step down is 1.2 foot. So plus 1.2 foot is equal to y2 plus, now q squared is going to be 30 CFS squared divided by 2 times 32.2 feet per second squared times a squared. And a is, at location 2, it's 8 times y2. And that is squared. So this equation only has one unknown. This equation, the only unknown in this equation is y2. But there's going to be more than one root. When we set it up, we consolidate things together. Like this term right here is 0.01781. The velocity head's pretty minor there. So if we just rearrange things, then we would have, if I put all of the numbers together on one side, 4.718 4.718 is equal to y2 plus 0.2184 divided by y2 squared. So you'll rearrange it and then transform it a little bit more. Like if we multiply each term by y2 squared, then what we end up with is y2 cubed minus 4.718 y2 squared plus 0.2184 is equal to 0. So this is the same equation as above. It's just kind of, we've multiplied like terms together, and we're trying to express it in terms of an equation that's going to have 3 roots. So now solve for y2. So probably, I think the Casio calculators have a specific mode that's set aside for solving cubic equations, and it'll give you all 3 roots. In this case, the roots are negative 0.211, 0.220, and 4.708. Now we can automatically throw out the negative flow depth. That doesn't have any physical significance. But the other 2 flow depths, each are depths that give you the right amount of specific energy. Like, what do those depths even mean? Like, these are the depths that have enough specific energy at 2 to account for the fact that you gained 1.2 feet of additional energy off of that drop. So we initially diagnosed that the flow regime at 1 was subcritical. So of these 2 depths, this is the supercritical depth, the shallow one, and this is the deep depth, the 4.708. So this is our new flow depth after the step down. So the water started at 3.5 feet, and it's going to transition to 4.708 feet. Now notice, it's pretty close to just adding together y2 and delta z. You know, 3.5 plus 1.2 is 4.7. Well, this is saying it's 4.708. It's not exactly linear, because there is some change in the velocity head as well. Specific energy isn't only because of depth. So we'll go through this process a lot, whether it's a step down or a step up, or the channel getting narrower or the channel getting wider. We're going to have cubic equations in each of those cases, and what we'll be looking at is the specific energy at 1, comparing it to the specific energy at 2. All right, that's all the stuff I've got for you today. Remember that we won't meet next week because of spring break, but I'll get homework 9 loaded onto Blackboard this afternoon. Do you have a question?
So was it just the maximum of 3 values that we received in the calculator?
Yes. In this case, we wanted the deeper of the 2 positive roots because it was the one that's associated with subcritical flow.
Okay, is there ever a situation where it would be the smaller?
Yeah. If we had calculated supercritical flow at 1 in the first part of the problem, then we would have chose this, the smaller depth. So we'll have an example next week, well, in 2 weeks, where we started off with supercritical flow, and so we'll choose the supercritical depth, the shallower.
On the recording, can you show your process?
Yeah, I'll pull that up right now.
All right.
Yeah.
Just so I can go back and look at it later.
Yep. Uh-huh.
Yeah, it'll show you X1, X2, and X3.
So this is showing the new depth.
I got it figured out.
Oh, good. So you registered?
Well, I haven't picked a date yet, but I figured out how
Okay.
to get to that.
Well, good. Yeah, I hope that you'll do well, and of course you get reimbursed when you pass.
Is that
So-
even if we don't pass it the first time, but it's after we graduate?